Okay, let me say a couple things about a couple of these homework problems. Okay, class is starting. Shut up. All right, so with number 11, you have a ball and socket joint. Here, and I'll just call that RC. And then you have two cable tensions. I'll call that TD because it's going to the point D, and TE. And then there is a weight or a force anyways at the midpoint going straight down. 3.6 kilonewtons. I'll just put that in newtons. And okay, so in these 3D problems that have cables, I think you pretty much always are just going to have to calculate the coordinates of a bunch of these points. So let's figure out the coordinates of A, D, and E. I mean, you might as well do them all, really. So I'm going to call that point C is going to be the origin. A is that is 2.4 meters. B is 1.2. D is negative 0.8. Positive 0.60. And E is positive 0.8, 1.20, and I don't think it gives any mass or anything. So this is all the forces, and we have 1, 2, 3 unknowns at the ball and socket joint, 2 unknowns here. So intuitively, what's going on here? Like, so there's, if you have 5 variables and the problem is solvable, then one of your 6 equations is going to be trivial, or it's going to be a linear multiple of the others. A lot of times you can look at it and tell which one of those equations is going to go away. In this case, none of these forces prevent this thing from barrel rolling, you know? And so we know that, what is that, the z-axis? We know that all of the moments about the z-axis are going to add up to 0. I mean, they're not going to add up to 0. They're all going to be 0. There's not going to be any moments there. So we're going to get a 0 equals 0 equation. And so we'll get 5 variables for 5 equations. Well, let's set up the table, and then if you want to keep going after that, we can. But let's just set up the table. So rho, force, moment. So first, this force RC. Okay. And then the 3600. If anytime, I mean, this isn't always like the most convenient thing to do, but it is true that anytime you choose your about point to be at the origin, your rho vector is just the coordinates where the force is applied. So, like, for example, so I have my about point here, And so my row vector for this 3600 is just the coordinates of B. So 0, 0, 1.2. And the force is 0, negative 3600, 0. And so the cross product is 1.2 times 3600. So that is 4320, 0, 0. And then we have those two cable forces. The row vector for both of them is just going to be the coordinates of that point A. So 0, 0, 2.4. And then this one is also going to be 0, 0, 2.4. And now we have to do the unit vector thing to figure out what those forces are. So for TD, the vector in the direction we want is going to be D minus A. So negative 0.8, 0.60 minus 0, 0, 2.4. So negative 0.8, positive 0.6, negative 2.4. And now we want the unit vector in that direction. Okay, so 0.8. And so what I got here for this unit vector is negative 0.308, positive 0.231, and negative 0.923. That's a unit vector in the direction of the force. So remember, you have to multiply that by the variable. And so this force is negative 0.308 TD, 0.231 TD, negative 0.923 TD. And then the cross product okay, 8, 0.231. And for that one, I got negative 0.554 TD, negative 0.739 TD, 0. And now we have to do the same thing for E. So the unit vector, not the unit vector, the vector in the direction of the force that's not a unit vector yet is going to be E minus A. So 0.8, 1.20 minus 0, 0, 2.4. And then the unit vector in that direction Bless you. Okay, so for this, I got positive 0.286, 0.429, and negative 0.857. And so this force is 0.286 TE, 0.429 TE, negative 0.857 TE. And then the cross product I got 1.030 TE, 0.686 TE, 0. And now you can look at what these equations are going to be. You have a bunch of non-zero stuff in each of the force components. So X, non-zero, 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 Y, Z. When you add up the moments, you have a useful equation for X, a useful equation for Y, but you can see that the Z components just say 0 plus 0 plus 0 plus 0 equals 0. And so that goes away, and you end up with 5 equations for 5 variables. Okay. Anybody want to see any more on that one?
Can you just throw it into an R table?
Sure.
Real quick?
Sure. Let's see. Thank you. Okay, so what's happening if you look at this from the side? Is you have a cable like this with a height of 5 feet, and you have a pulley here. Okay, so this distance is 10 feet. This distance is given as 2 feet. And you know, so both of these two, from this side view, both of these two parts of the cable lie along that same line. And so this small triangle is similar to this bigger triangle. Okay, and so the height of the big triangle is half of the length of the big triangle. So for the little one, that has to be half of this length. And so that distance here is 1 foot. So E is, it's going to be 0x it's going to be 10 minus 2 for Y, and then 1Z. And then F, let's call F the point where that force F is applied. That's just going to be 0, 5, 0. And the idea with that pulley is that that's the same cable that goes from D to E to C. And so that tension is going to be the same the whole way. So that's only going to give us one variable, but it's going to, you know, that single tension is going to apply 2 different force vectors to that pulley. Okay, so how do we want to isolate this? You know, we could just isolate this metal piece, and then that would let us calculate the tension in this, you know, just that short little cable that's attached to the pulley. And then we could isolate the pulley, given that we know this tension, and calculate the tension in these two. That's one thing we could do. Or we could isolate the metal piece and this little cable and the pulley and calculate this tension here, but we wouldn't calculate this one directly. And then you could go back and calculate the other one. I'm not sure if I did a solution for this, I'm not sure which one I would have, you know, done. I think they're sort of equivalent. But let's see, what do we want to do? Let's do, so free body diagram. Let's do we'll isolate that little cable and the pulley and a little bit of these two cables coming off of it. Okay. You don't have to do that, but this way is just going to let us calculate the tension in that DEC cable in one step. Okay. So we have a tension this way and this way. I'll call both of these T. It's the same cable. We have a ball and socket joint here. Call that RA. And then the only other force we have is the downward force F. And when we get to putting this in Newton's law, or when we get to putting this into the reduced row echelon form, or solving this system of equations by substitution, we're going to treat this like it's a constant and get everything else in terms of this value. Okay. So rho, force, moment. We'll start with RA. I'm going to put the about point at the origin. So that means that all of these row vectors are just coordinates where the force is applied. So RA has a row vector of zeros. The force is RAX, RAY, RAZ. Moment is 0. And now, well, I'll do F. So that row vector is 0, 5, 0. The force is in the negative Z direction. So 0, 0, negative F. And so this is negative 5F, 0, 0 for a moment. And then let's think of the cable tension to D. Like I said, the tension is going to be the same, but the directions are going to be different. So I'll start with the one that's going from the pulley to D. So a vector in that direction is D minus E. So 4, -8, 4. And then if you take the unit vector, do I know what that is? I think that is going to be positive 0.408, negative 0.816, positive 0.408. I've seen that one before. And okay, so these can get confusing because it's like you're using the same point for multiple things, but the row vector has to do with where the force is applied. So that's going to be at E. So 0, 8, 1. And the force vector is this unit vector times the cable tension. Okay, so this one I have 4.08 T 0.408 T and negative 3.264 T. And then for the one going to E, the row vector is the same because that force is at the same point. That vector, the only difference is we are going the other direction in X. Oh, I'm going, this is C, not E, right? All those distances are the same. It's like perfectly symmetric. It's just that that 4 is going to be in the negative X direction. And so we're going to get something that's like, you know, feel free to go through the steps, but this is just going to come out to be negative 0.408, negative 0.816, 0.408. And the cross product for that one is 4.08 T, negative 0.408 T, positive 3.264 T. That's what I got. And then the last one is that parameter force, that F. Oh no, we already did that. We're done. 1, 2, 3, 4, 1, 2, 3, 4. So yeah, we're done. All right, so I'm going to write this out just as a system of equations. So, because really, in one like this, some of your calculators will let you, in reduced row echelon form, will let you enter a variable in the constants column and calculate stuff in terms of the constant. An Inspire will, I think an 89 will, but I don't think 84s, 86s.
Really?
I don't think so.
I was gonna say, you said the Inspire can do that?
Yeah, I think you might have to define the variable somehow.
Okay.
Like tell it that that's something you want to keep as a variable in your
It might need
equations.
to be the CAS.
Oh,
that.
I have a CX. I don't know what that means, but I have a
So
CX.
then that's the same one. So
Okay.
Anyway, sorry.
Okay, so anyways, it would be nice if we could solve this by hand. And I think if I remember this one, some equations kind of reduce so that it's not too hard to just solve by hand. So let's see what we have. 0.408. Yeah, here's how they reduce. 0.408t minus 0.408t is equal to 0. And so this equation goes away. It's just 0 equals 0. And so we have a new first equation. Oh, it doesn't all go away. I missed this one. Plus RAX is equal to 0. So right away you can tell that RAX is equal to 0. The second equation says RAY minus 1.632t is equal to 0. The third one says RAZ plus 0.816t, I'm just adding those two together, is equal to, I'm moving the constants over to the other side, and F we're treating like a constant. Okay, that's the constant that drives this problem. And now for equation 4, we have 8.16t is equal to 5f. Equation 5 says 0.408t minus 0.408t is equal to 0. And equation 6, so these cancel, you get 0 equals 0, so this one does just go away. And so I'll call this one equation 5, I guess. And that says negative 3.264t plus 3.264t is equal to 0. This one again, those cancel. And so we only have 4 equations, and they're pretty simple to solve by hand. This one says t is equal to 0.613f. Okay, everything is going to be in terms of that f. Now, this one, you know, you can plug in our result from 4 into 3, and you get RAZ is equal to 0.5f. We already know RAX is 0, so this is the last one. 1.632 times 0.613. And you get that a y is, no, f. But yeah, I know I've done it before. I'm not sure what the syntax is you have to use, but you can write out an augmented matrix that has variables in it, but I think you might have to declare the variables like this is.
Yeah, I didn't. I just put an F and it worked.
Oh, okay.
Really? Like you can just put a letter into a.
Yeah, but I do have the CAS.
Yeah.
Yeah.
I included the constant line holding 0 and it made
Okay.
ultimate.
So let's let me do it and see if it.
Because I've tried to I've had trouble with cross products just because I'm bad at 3-component cross products, and I've literally put different values in, like a 2 for this one and a 1 for this one, so I knew which one went where.
Yeah, I know. I'll sometimes do that with like irrational numbers because you know that they'll like percolate through everything and still show up. So treat t like it's square root of 2 or something, but
Yeah,
that doesn't seem ideal.
it's not.
Oh, I just did it for 5 equations. I guess let's do it for 6. Okay. So 1, 2, 3, 4, 5, 6. And we have R, A, X, R, A, Y, R, A, Z. 1, 2, 3, 4, 5. No, we only have 5. Well, I was just going on the. Yeah. Okay, so we only have 5 variables if you just look at the free body diagram. So because f we're treating as a constant, I guess that's because 2 of these equations are linear multiples of each other. I guess that's treating these 2 equations like they're linear multiples of each other. Well, all right, so let's just put it in like that and see what happens. Oh no, 4 variables. Yeah, like you said. It's not funny. 1, 2, 3. Then we got t. Then, okay, 1, 2, 3. The constant. Okay, so it's RAX. We got 1 of those, no constants. The second equation says RAY, negative 1.632. The third one says 1 RAZ. T is 0.816. And the constant is F. And then the fourth one says 8.16 T, and the constant is 5F. Maybe that's true. Maybe I've only used the 89 and done that. Okay, any questions about that? Okay, we forgot to have class today.
I do have a question about that. So I haven't done that one yet, but if you could you just isolate just the 1 cable And since they're two
Yeah.
parallel, just treat it as one cable going straight to their midpoint.
In this case, it turns out you can. It's not like totally obvious to me why that would be, but if it's obvious to you, then you can do it. I mean, it would come out as exactly the same math as not dealing with this cable at all, just
Yeah.
dealing with this cable.
Yeah.
And then if after that you wanted to calculate the tension in this cable that goes through the pulley, you could do that as a really easy separate particle problem, you know?
So that, okay.
So that would
Because
work.
to me that, I guess I didn't even think about isolating it and using two cables.
Yeah, right, right. But yeah, I think probably the more obvious way to go is just isolate the bar, whatever this thing is, calculate the tension in that cable. And then if you know that you're trying to figure out the tension in the other cable, then just do a particle statics problem after the fact.
And then so the force in that particle statics problem would just have a reversed unit vector of the one that you found from B to E.
Right,
And then you just have those two going off.
exactly,
Respective directions.
exactly right, yep.
Cool.
Okay, talk to you later.